Hello everyone, I am Prajwal from Sri Venkateswara College of Engineering. Today we are going to study about Hadoop performance tuning. Introduction for Hadoop performance tuning. Hadoop is an open source framework for distributed storage and processing of large data sets using cluster of commodity hardwares. While Hadoop provides a scalable and fault tolerant platform for big data processing, optimizing its performance is a crucial to ensure efficient processing and resource utilization. Hadoop performance tuning involves configuring various parameters and setting to achieve better throughput, reduce job execution time, and provides all over efficiencies. What are the strategies and techniques for optimizing the performance of Hadoop clusters? Cluster configuration, Hadoop configuration, HDFS configuration. Cluster configuration. Ensure that your cluster hardware is very well configured. This includes optimizing the number of and specification of nodes, balancing resources such as RAM, CPU, and disk across the cluster, and choosing appropriate network settings. Hadoop configuration. Just Hadoop configuration parameter based on the characteristics of your data and workload. Key configuration file includes core site XML, HDFS site XML, and MapRed site.xml. Tune parameters such as block size, replicator factors, and heap size of the name nodes and data nodes to suit your data and cluster size. HDFS configuration. Optimize the Hadoop distribution file system for better performance. Adjust the block size based on the size of your data and nature of your workload. Smaller blocks may be more suitable for larger number of small files. Some other techniques are YARN configuration, job configuration, data serialization. YARN configuration. YARN is nothing but yet another resource negotiator. Is the source of management layer in Hadoop. Configure YARN parameter in the YARN site.xml file. Adjust the memory location for container size, queue configuration, and other settings to optimize resource utilization. Job configuration. Optimize job configuration based on the specific requirement of your MapReduce jobs. This includes setting of the number of mappers and reducers. Choose appropriate comprehension decodes and configure execution. Data serialization. Choose efficient data serialization format, example Avro and Parquet, to reduce the amount of data transfer between nodes and stored in HDFS. This can significantly improve job performance. Speculative execution, data compression and serialization, network optimization, regular updates and maintenance. Speculative execution. Enable speculative execution for MapReduce jobs to mitigate the impact of slow running tasks. This can help improve all over job completion time. Data compression and serialization. Use efficient data compression algorithm to reduce the amount of data transferred over the network and stored in HDFS. Use serialization format like Avro and Parquet to improve data read and write performance. Network optimization. Ensure that the cluster nodes have high speed and low latency interconnect to facilitate efficient data transfer between nodes. Minimization of Minimize the impact of network latency by co-locating data and computation whenever possible. Regular updates and maintenance. Stay informed about Hadoop release and updates. Regular update and Hadoop distribution to benefit from performance improvement and bug fix. Common performance bottlenecks. Hadoop cluster can face various performance bottlenecks due to factors such as hardware limitation, misconfiguration, inefficient job design, and data related issues. Identifying and addressing these bottlenecks is crucial for optimizing the all-over performance of the cluster. Here are some common performance bottlenecks in Hadoop clusters. Hardware limitation. CPU bottleneck. Inadequate process power can lead to slow job execution times. Ensure that node is the cluster to have sufficient CPU resource. Memory bottleneck. Insufficient RAM can result in frequent data input and output, reducing overall performance. Adjust JVM, heap size and monitor memory usage. Disk bottleneck, slow disk speed or high disk contention can impact read and write operation. Use fast disks and distributed data even across nodes. Network bottlenecks. High latency network congestion. Slow and high latency network connection between nodes can affect data transfer speed and job performance. Optimize network infrastructure for low latency. Network congestion. Insufficient bandwidth can lead to congestion affecting communication between nodes. Ensure adequate network bandwidth and optimize data locality. HDFS bottlenecks. Small block size replication overhead. Using a small HDFS block size for large files can lead to increased metadata overhead and insufficient data processing. Adjust block size based on characteristics of your data. Replication overhead. High replication factor can result in increased network and storage overhead. Balance replication for fault tolerance while minimizing unnecessary data duplication. YARN bottlenecks. Resource contention, node manager overhead. Resource contention. Inadequate allocation of resource by YARN can lead to resource contention among applications. Adjust YARN configuration including container size and queue settings. Node manager overhead. Overloading node manager with too many containers can impact performance. Monitor and adjust node manager configuration. Map reduce bottlenecks. Insufficient job design. Poorly designed MapReduce jobs with inefficient mappers or reducers can lead to longer job completion time. Optimize the design of your MapReduce jobs. Data skew. Uneven distribution of data among mappers or reducer can result in one or few tasks taking significant longer than other. Address data skew through partitioning and proper key designing. Other few common bottlenecks are data related bottlenecks, monitoring and logging overhead, JVM garbage collection. Data related bottlenecks. Data locality issues, data skew. Data locality issues. Inefficient data locality can result in higher network traffic and slower job execution. Optimization data placement to ensure that the task runs on nodes where the data is stored. Data skew. Uneven distribution of data size among nodes and partition can lead to uneven task execution time. Address data skew through data pre-processing or redesigning. Monitoring and logging overhead. Excessive logging. Too much logging or monitoring can introduce overhead. Configure logging levels appropriately and use monitoring tools judiciously to avoid performance impact. JVM garbage collection. Frequent garbage collection. If the Java virtual machine performs frequent garbage collection, it can lead to pause and degrade job performance. Tune JVM settings to optimize garbage collection. Conclusion. In conclusion, Hadoop performance tuning is a critical aspect of ensuring optimal and efficient operation to Hadoop cluster. The process involves addressing various factors including hardware configuration, Hadoop and HDFS settings, job design, and network consideration. By following the guidelines, organization can ensure that their Hadoop cluster operate efficiently, deliver optimal performance, and effectively handle the challenges posed by large-scale data processing load works. Continuous monitoring, updation to change, and knowledge sharing are the key to maintain and perform gain achieved through the tuning process.